Hello everyone, my name is Tarush Shankar and I belong to the group of MRI Motion Actuator. My team members are Kyle, Aryan and Andrei, and our client for this project is Dr. Kawchuk. For our team, we have Dr. Steve Knudsen as our technical advisor. Lower back pain is a menace to the society. It contributes to health, economical, and a lot of social problems. To counter this, our team has come up with a mechanical device which would help diagnose lower back pain more accurately.
Hi, I'm Aryan, and I'd like to go into details about our project's functional and performance requirements. So for our project, we wanted to create an actuator that is capable of producing vibrations up to 150 hertz based on an eccentric mass of 5 to 50 grams. And we also wanted to achieve an actuator that is completely MRI safe. We were able to achieve these requirements pretty well. However, certain parts like the metal bearings inside the actuator are not MRI safe due to budget constraints.
Hello everyone, I am back and I'm here to show you the system design of our device that we have made. Our system design consists of many components together. To understand its working, I'll show you each component at a single time. Over here we have the Raspberry Pi. Our Raspberry Pi runs and interprets a Python motor script. The Python script that we have made takes in the user input of the frequency, and this interprets the script and translates the signals to our stepper driver. The stepper driver is powered by our power supply over here, and the stepper driver receives signals on a two-way basis. It sends signals based on the motor script that we run to our actual motor, which causes the thing to rotate. It also receives feedback signals from the motor to get the positional feedback and correct itself in case things go south. Over here we have a 3 feet long drive shaft which is connected to our main component of the actuator housing. This is made from using a 3D printed filament of PLA, and it houses a 3D printed eccentric mass as well. We use 2 bearings for our design in order to hold things in its place. And this is our entire system in essence.
Hello, my name is Kyle Wiskel, and I will be presenting the motor script as part of our demo, and then we will demonstrate the motor in action. So the motor script is very simple. The Raspberry Pi is just connected to the motor driver, and we have the step size set up as 1600, so that means there's 1600 steps per 1 full rotation. So this is a medium value. You can get a lot more precise, and you can also get less precise. So the frequency, the user can enter the frequency, and the motor will simply rotate based on the frequency. So how that works is it outputs a high value and then sleeps for step size times the frequency, 1 over step size times the frequency. And then it will go low and do the same thing. So that means that if you enter 50 as a value, it will rotate 50 times a second. So to demonstrate, we simply run, and then we can enter our value. So in the following example, Andrei will show the motor running at 150 hertz.
Hi, I'm Andrei, and today I'll show you what happens when we run our script. So currently you can see that the motor is not spinning since we have run our script. So right now we'll run our script. As you can see, the motor is now spinning this 3 feet flexible drive shaft, and in turn it is also spinning this 3D printed eccentric mass. Although very subtle, you can feel vibrations on the housing.
Now let's go into some details about what worked and didn't work for our prototype design. First of all, 3D printing and making our own custom CAD drawings for our actuator helped us achieve the desired functionality out of our device. We were able to adjust the dimensions of our components to fit the other non-customizable parts like the bearings and the rotating shaft. It also allowed us to learn more about the process of computer-aided design, which is a central part of many engineering projects. The eccentric mass within the actuator went through a few iterations as we first decided to build a mostly hollow eccentric mass, which we could modify by attaching it to a central rotating axis. We later decided to include the axis within the eccentric mass itself and filled out the cavity within the eccentric mass to meet the minimum weight requirements. However, the hollow design allows for adjustable weights by adding or removing sand within the eccentric mass cavity. These components put together allowed us to get the actuator to vibrate with the desired frequencies. In terms of what didn't work for our design, we ran into the issue of real hard time constraints of operating the device. Although the Raspberry Pi microcontroller allows for ease of use and timely shutoff, using a real-time embedded system like the Xilinx Zybo Z7 board would be a better alternative, as it would allow for better synchronization with a MRI machine. The noise within the closed-loop stepper motor is also an undesirable side effect of our prototype, which contributes to the inconsistency of vibrations. Our actuator also has minor design flaws within the bearing housing that should be improved upon in future iterations to minimize inconsistency of vibrations.
There is future work that can be done to improve upon our MRI Motion Actuator. The first step, as discussed already by Aryan, is to use a real-time operating system. An example of this is the Zybo Z7 board. It was difficult to use this in our prototype as it is an expensive board that costs over $400. But by having a real-time operating system, this will allow for better control of the motor and be able to meet hard real-time constraints. By also having a real-time operating system and meeting hard real-time constraints, this will allow interfacing with the MRI machine. To actually use this product to diagnose back pain, the actuator vibrations have to be synchronized with the MRI machine captures. It would therefore be necessary to use a real-time operating system, as it would allow control of the motor and interface with the MRI machine, and so that they're synchronized. In addition, this was also mentioned a bit by Aryan, but currently our drive shaft is a flexible drive shaft that isn't MRI safe. It was about 3 feet in length and cost about $100. There are possible solutions for this. One of them is we want to ensure that the drive shaft is MRI safe but also cost efficient. A solution would be to construct this in-house and design a 3D model of interconnected lengths of flexible drive shafts, potentially 1 feet, 3 feet. Then you can make it as short or as long as you need it by interconnecting them. This could then be created using 3D printer or other techniques by different plastics. This will ensure it's MRI safe and allow for longer length, as well as being cost efficient. In addition, the housing is very chunky and would need a better form factor and potentially smaller. It would need to go under a patient's back without being too uncomfortable. Therefore, a more compact and curved solution would be needed. Finally, a friendly GUI would allow for easier use by professionals. A possibility is, if we're using the Zybo Z7 for real-time constraints, it could interface with a Raspberry Pi, which would provide the GUI and potential network capabilities. This could then send control signals to the Zybo Z7, which will then run in synchronization with the MRI machine. An addition to this GUI could be allowing for motion profiles, where the user could select different motion profiles, different speeds of motor under different patterns, potentially rotating in different directions. Now that we have discussed the future work, I will pass it off to Andrei to do the conclusion of our presentation.
To quickly summarize our project, our group was able to successfully develop an MRI Motion Actuator unit that was able to meet the performance and functional requirements that our client has provided for us. we were able to produce a successful proof of concept with a hardware unit that is able to vibrate at a frequency that is specified by the user, and an easily exchangeable eccentric mass within the actuator. From here on, our prototype can either be used in limited situations in a clinical setting, or it can be further improved upon in many ways, such as a longer drive shaft, or an added friendly GUI, or in any way that our client would like. Overall, the project can be considered a success, as our group was able to create a design that can be of great use in the medicinal field, more specifically in spinal research. Before we finish the presentation, we would also like to extend our gratitude to our sponsor, Dr. Greg Kawchuk, who has helped us extensively throughout the entire process of our project through providing us with useful information, relevant research papers, electrical components, and in many other ways. This marks the end of our presentation. We would like to thank you for your time and attention.